So we're going to start with a pretty quick run through of the SolidFire product for those that aren't familiar with it, some of the key differentiating features in it. And then in the second half, we'll get into really the architecture underneath these features. But we want you to understand before we talk about how great the architecture is, what is it that we can do that has all these customers buying it? Why are they buying this instead of any other flash or disk-based storage system that can do it? What is so unique to SolidFire? So SolidFire at a high level, it's a scale-out high-performance storage system. So we're primary storage. We're a scale-out system. We'll talk more about how we scale out today. It is the largest and fastest all-flash system on the market today. That's not necessarily the most important thing about us, but we certainly think we have claim to that with scalability to over 100 nodes in a single cluster, up to 3.5 petabytes of capacity and 7.5 million IOPS. All industry standard hardware, 10 gigabit Ethernet for the connectivity. We also have fiber channel that Adam will be talking about, but 10 gig E is all we use for the connectivity. Nothing proprietary, nothing too exotic, all 10 gigabit Ethernet. Very rich feature set. We'll be talking about some of these in more detail, but certainly we think we have the broadest feature set in the flash space today for an enterprise storage system. But when we talk about the things that really make SolidFire unique, they really fall across these 5 key areas, areas that we think are very important in the next generation data center. Scale out, guaranteed performance, automated management, high availability, and inline efficiency. So let's talk about scale out first. SolidFire uses a node-based scale-out architecture. The building blocks are these 1U x86 nodes. Sooner or later, we might actually have one show up in this room. I think we're waiting for FedEx.
Right.
All right, so we'll bring that in later, and you can poke around on it. 1U x86 servers, CPU, memory, 2 10 gig ports, 10 2.5-inch MLC SSDs in it. Again, nothing particularly exotic. Cluster them together over a 10 gigabit network. All of our software magic running on top makes a single logical managed storage system, a single pool of capacity, and a single pool of performance in this cluster. Of course, the great thing about being scale out is that you can then add additional nodes and add additional capacity. And yes, we can actually do this, and yes, this works. And it's been in the product from the beginning. Completely non-disruptive. Data is redistributed in the background. We rebalance the capacity, rebalance the performance non-disruptively, and it happens pretty quickly.
How fast is pretty quickly?
So it takes lower priority to active I/O, obviously, so it depends on how heavily loaded the system is. But and the other thing you'll find is that the larger the system is, the faster this actually happens. But in general, minutes. So you can typically add a node within 15, 20 minutes. And if you're adding multiple nodes, it does it all in parallel, so it actually doesn't really take much longer to add multiple nodes to the system. The really cool thing about this that we've actually been surprised to see is that customers are almost as excited about the scale-out capabilities as they are about the scale-down capabilities, which seems strange because people always just get more data, right? Well, yes and no. Yes, they're getting more data, but sometimes the data is going to different places, different locations. Maybe a different data center, maybe somewhere else within the data center. And what we've actually seen is that the ability to take a SolidFire cluster and just as easily as you can add nodes, remove nodes from it, and send them somewhere else, build another cluster. We've seen a couple real-world examples of this where in one case, a customer had multiple data centers. They had more capacity than they needed in one. They were running short on the other. Now, if we were any other storage company, what would they have to do? Well, you can't really do anything about this, so I've got to buy more storage from me.
I don't know why you think that's a good thing, Dave.
I don't know, but the customers seem to like it. So what did they do? They removed a node from one. They shipped it a couple countries over. This was in Europe. They put it in the other cluster, and they were up and running in 24 hours. And that level of agility is really important. Another example we saw is they had built a very large cluster. They decided that they actually wanted to move a bunch of that data somewhere else. They took out part of the nodes of the cluster, built a second cluster, migrated the data, and they had already split that. And again, this is something that is really cool about scale-out storage that you just can't do with a traditional array. You can't take a VNX or a VMAX, take a chainsaw to it, and send half of it somewhere else.
Well, you can. You can't expect it to work.
Yeah, it just may not work too well when you're done.
It is good stress relief, though.
Yeah.
So can each node be seen as a start for a new cluster then?
Absolutely. So you can take minimum of 3 nodes or 4 nodes to start a cluster, remove a couple of them, put them together, and as we'll talk about later, you can now mix and match nodes of different capacities and generations in a single cluster as well. So lots of cool stuff there. So one of the great use cases for that, I don't want to steal too much of Adam's thunder, is you start off with a current generation of node, maybe you start adding in denser nodes, and then later on you pull out those smaller nodes and put them in a lab, use them to spawn another cluster somewhere else. But really, really cool. And that's when we talk about storage agility. That's a lot of what we're talking about, being able to use and repurpose and deploy your infrastructure in ways that previously had not been possible.
What are you using to measure IOPS?
So we tend to use a tool called VDBench, mainly because most of the other tools like Iometer can't actually push the performance that we actually can push through the system.
We have a question from Twitter about, could you theoretically run a 1 or 2 node cluster?
What's that? Could you? Not really. So we need 3 nodes for a quorum, and our recommended best practice is 4 or 5 nodes. And it mainly has to do with, as we'll talk about with high availability, the ability to sustain failures and keep running. You know, it's something where we recommend a 4 or 5 node starting configuration. If you look at where the Scaleout architecture positions us in the market, you can draw the disk-based guys out there, upwards of petabytes of capacity, not that much performance. The other all-flash guys down here in the bottom left corner, so millions of IOPS, and this is just straight from their spec sheets, but really not that much capacity. Typically, most of these guys have 100 terabytes or less effective capacity available today. So again, very good for performance-constrained applications, point solutions, places where you're just trying to drop something in and make an application go faster, but not really good at the core of the infrastructure, places where you really need scalable capacity. SolidFire, and we have 3 nodes available today, reaches the capacity of the disk-based systems with the performance of the all-flash systems. And being a scale-out system, you can land anywhere on any of these lines you want. And now with our mixed node capability, you can really land anywhere in here that you want as well. And our architecture is flexible enough that you can expect over time there'll be lines that go like this, lines that go like that, and we will encompass a broader and broader set of capacity and performance over time.
Dave?
Yep.
The ends of those lines are the 100 node cluster.
100 nodes. Yep.
Yeah, but the ends of everybody else's lines are the maxes, the max, right?
Max
Yeah,
you can buy
but-
from them too.
But I'm just, you know, I'm just applying the.
Yeah.
They
Fairness
haven't actually
principle.
got 100 node.
Well, like I said,
clusters.
we test at about right here today.
Right, that's-
Most of our customers are about right here today.
Yeah.
But the important thing about that is most of our customers are beyond where they could get
Right.
without having a bunch of those guys.
Yeah. Actually, that's exactly what I wanted you to do. Is go and here's where we tested too.
Yep. So the second thing, and this is probably the thing that we historically have been best known for, is our guaranteed performance capabilities, our guaranteed quality of service. And if we have time in the demo section at the end, we'll actually demo some really interesting and new things we're doing with this combined with VMware. But this is really enabled through something we call an architecture performance virtualization. We get in the architecture section, I'll touch on some of the how we do this. But the simple way to think about performance virtualization is separating the provisioning of performance from the provisioning of capacity in a storage system. Basically, every other storage system on the market today, you provision capacity, and how you provision that capacity determines the performance you get. What type of media you provisioned it on, how many disks are in there, how fast those disks are, what RAID level they have, how fast the controllers are in front of them, how much cache you have sitting in front of those. Through the combination of all that, that solution and that volume and that particular application will get some level of performance. The really complicated thing about that is that performance can easily change tomorrow if you go and provision something else in that same configuration. And so performance management has always been very challenging in storage. And approaches to quality of service before this were always fairly basic. They were typically one of 2 approaches. One was rate limiting, where you just say, you know what, I want to make sure this volume doesn't go any faster than this so that he can't be too much of a hassle to the other things on the system. And that's okay, but the real problem with rate limiting is, it's nice for the other guys. It doesn't really help the guy that's being limited because, he knows what his maximum is. It doesn't tell him anything about his minimum. And actually managing that across a lot of different applications can be very challenging. The other approach is prioritization. And prioritization works well when you have a very small set of constrained applications where you know the relative priority of all of those things, and you can make relative judgments to make sure that the high guys are high and the low guys are low, and it's not really a problem if the high guys are noisy and cause problems for the low guys. When you move into these more cloud-like environments, number one, you've got a lot more applications, and even large virtualization environments have this problem. You've got a lot of applications. It's hard to assign relative priorities to all of them. Everybody thinks their thing is the most important. And in the service provider case, a lot of times they don't even know what the applications are. And so maybe they can make somebody pay more to be high and less to be low. But if they can't tell the high guy how fast he's going to go, he's not going to pay more than that. So if you can't actually give them metrics and numbers and minimums and SLAs around performance, the quality of service isn't really that meaningful. And so we've designed our system so that you can actually allocate performance independent of capacity for every volume in the system with a very fine-grained model that has minimum, maximum, and burst. And of course, that minimum is the key, actually knowing what minimum level of performance you'll be able to deliver for that volume at any given time.
Sometimes the max is important, so rate limiting can
It
be
is.
useful when you want to make sure that people are only getting what they pay for.
Exactly. And so particularly in the service provider realm, actually saying you paid for 11,000 IOPS, you're going to get on a consistent basis a max of 11,000 IOPS. If you want more than that, pay me more. But because hard rate limits actually cause problems for a lot of application workloads, things that are very spiky, if you think about like a VDI boot storm or a database checkpoint or something that you don't really want huge latency spikes on, we have a burst capability as well. We use a credit-based scheduling mechanism, and if you're running under your maximum, you build up credits, and you can actually burst for a period of time higher than that, similar to the bursting models that you can get in network quality of service. Again, all kind of very new and interesting on the storage side of things. The performance allocation is also completely dynamic. So you can take a volume that had 1,000 IOPS, turn a dial, give it 5,000 IOPS, and literally within seconds,
Can
you'll
you
see
see that
performance
back?
change.
You just said you can show what someone gets as a minimum, but you can burst.
Yep.
But you might want to know what the exact amount was after a period of time.
Yep.
To make
And
sure
so,
you.
exactly. So part of our API and reporting capability is the ability to get the data out that includes data on how much did they actually do. Maybe you want to do usage-based billing and charge back based on what they actually did, not what was allocated to them. You can measure if the SLAs were met. Because, and our system gives you a lot of different options for this. You can under-provision the minimums, the sum of all the minimums. You can over-provision the minimums. You can do a lot of different things to both help yourself or get yourself in trouble. But our reporting actually can tell you back out of it, did everybody get what they were guaranteed? Did everybody get their minimums like they were supposed to, or for some reason, did they not? And you can actually see that in the reporting.
Dave?
Excuse me, can you do?
Yeah.
Sorry. Okay. Can you get a pool of LANs and make the QoS for that pool of
Yeah,
LANs?
great question. Not today. Now, where we typically see that being done is like for a tenant or a customer. In a VMware environment, what's usually done is creating a data store, having the QoS on the data store, and then they really do get a pool for all of the virtual machines in that data store. Arbitrary grouping of any LUN on the system into a QoS group is something that's a roadmap item. We don't have a lot of demand outside of VMware for that today, though. So.
Yeah, okay.
Okay, Dave.
So-
Yep.
The tables suggest that you can adjust the number of IOPS per block size. Is that correct?
Well, not exactly. So when we talk about IOPS, just to kind of keep things simple, we talk about everything in terms of 4K IOPS.
Okay.
But what you're seeing down here is obviously different IOPS have different weights.
It translates it automatically.
And it translates. It tells you. So if you know this, your average, and this is totally based on averages, if your average workload is based on 16K IOPS, this is what that actually translates to. And that's really important because some other approaches to quality of service that just bound it based on IOPS, if they do 1 meg IOPS, they can, even though you only gave them 100 IOPS, they can crush your storage system.
Yeah.
So it's very important that you actually expose, this is how what we call the QoS curve works at different IOPS sizes. So it's not linear because there is some savings that we get from larger IOs, but there is additional cost. Okay. And really where we see this in practice, and this is a great illustration of this, and we do this demo all the time, when you have an environment that's relatively noisy, sharing a set of resources could be a storage controller, certainly very apparent when you're sharing the same set of spindles. You have a couple of guys that go crazy, start sending a workload on it, everybody else gets affected. In this demo, we turn on the SolidFire quality of service. We put, for each volume in the system, we dial it in this case, to 4 different performance levels. And literally within a few seconds, everybody gets exactly what they want, exactly what they're paying for, whether it's a service provider model or an internal chargeback model. And if an application that's down here at performance 3 is getting maxed out and really needs more, you can literally turn a dial and give it whatever performance level you want.
So Dave, just to clarify, maybe I missed it. What's the grouping for the QoS?
Quality of service is on a volume or LUN.
So when you say volume, what does that
So
mean?
it's basically the same thing in ours. It's a LUN. So what we see as a virtual disk now, it's things like VMware like to put many disks inside of that. If we get to the exciting demo at the end of the day, you'll see actually how we break out and do it on
that
a
was one of the things I couldn't
VM
work
level.
out from the web.
Yeah,
was
with
just
something like
how do you group
Cloud
it
Stack or OpenStack, the volume level corresponds directly to a virtual disk level. With VMware, it tends to correspond more to a data store level, but there's some interesting things we're doing there. I don't want to ruin my surprise.
Uh-oh.
Sorry. All right. Any other questions on the quality of service piece? It is really cool. The third thing, shared nothing high availability. And we'll talk more about this when we get into the architecture in terms of how this contrasts with other approaches to HA. But suffice it to say, the mechanism we use for data protection, high availability in SolidFire involves not a traditional RAID algorithm, but a distributed replication algorithm that distributes redundant blocks within the cluster so that we have multiple copies of the data. The data is not replicated within a node, but across multiple nodes, allowing us to survive loss of individual drives as well as entire nodes. And importantly, allowing us to very quickly and very easily redistribute data when a failure occurs. And that's not a perfect illustration because it's actually a meshed rebuild process. When a node disappears, the data that was on that node is actually spread, the other copies of it are spread across the remaining nodes in the system, and we do a meshed rebuild process. And this literally lets us rebuild from a drive failure in about 5 minutes, which is extraordinarily fast. And the scary thing is, as the cluster gets larger, that gets faster. On a really big cluster, we can do it under a minute. Extremely, extremely fast. And once that rebuild is complete, we've restored the full redundancy in that system. And you can sustain additional failures. And when a failure occurs, all we're basically consuming is free space that was in the cluster. There's no dedicated spare drives. There's no dedicated spare nodes. The system just rebuilds as if it was a smaller cluster. One drive smaller, one node smaller, whatever failed. And the really cool thing about it is we handle every failure in the system basically the same way, whether it's a hardware failure in a node, a hardware failure in the drive, a backplane failure, a network connection failure that makes a node unavailable, even a software failure that something is crashing and it just can't restart and doesn't come back up. We treat it the same way. We kick it out, we rebuild, and we restore the redundancy in the system.
So the redundancy is one level replication or 2 or 3 or?
Today it's 2. We will have an option for 3 in the future, but based on our metrics, the speed at which we rebuild means that our essentially 2-way replication has equivalent or better chance of data loss than RAID 6 in a typical system.
So what is the interconnect you're using to manage that between
10,
the nodes?
10 gig Ethernet. So all of these nodes are connected with 2 10 gig Ethernet ports, and that's what's used for both the storage network as well as the cluster interconnect.
Okay, so that means that the interconnect would be some sort of 10 gig network, pretty much anything that you can.
Yeah, typically you've got a cluster plugged into 2 10 gig top of rack switches, and that's it.
Yeah. So you're limited by the number of ports that you can plug into, and then you'll have certain latency steps based on how many.
Yeah, depending on how you build your network.
Yep.
And like I said, typically a cluster is plugged into one switch, and particularly with the 72 port 10 gig switches available today, you can build really large clusters even on a single switch architecture. Yep. But you can also go leaf spine, add one more hop, and still have very good latencies.
Customers are supplying their own networking hardware for this, right?
Exactly. So we are network agnostic. We work with Arista and everybody else.
Arista switches.
Well, true.
We like Arista, though.
Yeah, well, clearly.
It's really well.
But
Got to pay the rent.
that actually solves a problem in that you don't have to play the game of, you guys like Arista, but my networking silo likes Cisco and screw Arista, and we don't have to sort of negotiate that. And fine, use a Nexus, we don't care.
Yeah, we don't, and we've worked with pretty much everything under the sun in the field today, and it all works pretty well.
Cool.
So.
Do you see the 2-port 10 gig as a bottleneck yet?
It's not the bottleneck yet. We can see it heading towards being the bottleneck as other parts of the system get faster. We actually have 40 gig in the lab today.
Okay.
And with the price of 40 gig ports and switches coming down, it's a reality pretty soon here. So,
okay.
Yeah.
Thank you.
Now, I would say that even when we see it approaching the bottleneck, it's only a bottleneck of the theoretical, the max throughput of the system.
Yeah.
Most customers probably won't be approaching that anytime soon, so even then they may not choose to go to 40 gig. Next to us, very core to the architecture, inline efficiency, compression, deduplication, thin provisioning. We'll cover more of the how in the architecture session, but suffice it to say the architecture was designed from the ground up around being able to do these inline, in real time, without significant performance impact. So these are always on. We do global deduplication across the entire cluster. So any volume, any piece of data, deduplicated across the entire cluster, real-time compression.
That's a good one.
Space-efficient snapshots, cloning, all of that stuff integrated with this as well.
And the hash algorithm is?
Skeen, 256. Good question. I followed the discussion on that earlier. So you guys have beat that one into the ground.
Can we talk about it for like 15 more minutes?
That would be great.
That would make me want us to be killed by an asteroid before there was a hash collision.
Yeah, and we definitely would be. I've run the numbers. Just a very, very simple comparison, and we can give you all the breakdown on and exactly what we did here, but to actually demonstrate the efficiency of both the data reduction, and this is, by the way, very conservative estimates for data reduction, 2x compression, 2x deduplication, so nothing, 20x ridiculousness or anything like that, against a traditional disk-based, and this is actually, I think, a hybrid SAN configuration, and what you actually get for an equivalent amount of capacity in terms of space, power, cooling, reduction, and performance increase. So, a rack versus 5U, 52,000 IOPS versus 375,000 IOPS, 90% less rack space, 78% less power and cooling, et cetera, et cetera. And we've priced this out, and it's pretty competitive. There's not a huge difference in price between this. So particularly when you look at guys that are deploying this at massive petabyte scale, the operational savings, cost savings add up real quick. So yeah, the OpEx savings, and that's important to point out, the OpEx savings are really gravy on top because, again, the CapEx is pretty comparable to that configuration. From a management perspective, we've really done a couple of things. One is drastically simplify it. And this is something I talked about in the software-defined data center section the other day. You can't automate anything that's overly complex. The best you can hope to do is put a layer of indirection in it that hides the complexity and simplifies it, but it's actually better to start with something that's far simpler to begin with. And so we've done that. You get a global unified pool of capacity, a separate global unified pool of performance. You just provision out of that your individual volumes. As you scale your cluster, those pools just get bigger. There's no magic. There's nothing fancy. There's no separate pools of different capacity types. There's no separate RAID groups. There's no separate RAID levels. There's no aggregates. There's no volume groups. There's no 5 levels of things you need to set up. You plug in the system, you turn it on, and you just start provisioning. Automatic load distribution across the cluster, no hotspots. Whether the cluster gets bigger, gets smaller, you're never having to manually place or reprovision things. Single-click provisioning of volumes, very, very simple. And that self-healing capability we talked about.
So the automatic load distribution is by your hash kind of algorithm or something like that with a consistent hashing?
Yeah,
across the
so
nodes?
the data and load are distributed through the hashing across the cluster. Yep. We also have some things that take into account when you have variable size nodes and other things to keep things balanced.
How is the load distributed by the hash algorithm?
Good question. So the way to think about it is the hash algorithm is random. It distributes the blocks across the cluster in a random fashion. And it actually ends up distributing the load in a very random fashion as well. You could say, well, what if the actual load coming in isn't random? Doesn't really matter. Unless they're just sitting there hitting a single 4K block, even if they're hitting, say, a 1 meg section of really hot data, that 1 meg section is actually going to already be distributed across the entire cluster. So we don't have to do anything special to distribute or redistribute based on load. The distribution of the data actually ensures that even distribution.
How do hosts access the cluster then?
Yeah. So the connectivity is iSCSI. We have Fiber Channel very soon. Adam will talk about that. But just to keep it with iSCSI for a second, they connect to a specific volume through iSCSI. We have a redirector service that balances those connections across the cluster.
Does that run on a single node, or is that?
It does, but it fails over to other nodes. But the redirector service doesn't handle any I/O. It just redirects connections to other nodes. They make the connections to the individual nodes. And then they do their I/O through that particular node, and we talk through the back-end network to the rest of the cluster.
So the host talking to all of, possibly talking to all of the nodes, or just a subset of nodes? Or?
Yeah, so it depends. For a single volume, they're talking to a single node.
Okay.
If they have multiple volumes, those connections will probably end up getting spread across multiple nodes.
Okay, and then so a single volume is associated with a single node, and then the node manages any other distribution?
Exactly. So the actual data then is distributed over the back-end network.
Okay.
Yep.
So it's been my experience that a lot of enterprise customers have been leery of iSCSI for whatever reason for Tier 1 applications.
Mm-hmm.
You guys have people running Tier 1 applications.
Absolutely. Yeah. Oracle, SAP, you name it, and a lot of them in the same one. And I think they've been leery for good reason in the past. iSCSI has a little bit of a murky history, but a lot of that has changed. Particularly the move just from 1 gig to 10 gig has been a big part of it. People actually building decent networks as opposed to just putting it in, plugging it into the wall into a very poor network is another piece of it. The maturity of the iSCSI initiators has gotten dramatically better, and compatibility is really a non-issue at this point, which is another big piece of it. And the other thing that I think has tainted iSCSI to a certain extent is the fact that iSCSI was associated with lower-end storage systems. They were less powerful storage systems, and so people had performance problems. They upgraded to a fiber channel system, and everything got better. It may not have actually been the protocol choice per se. It might have just been the fact that they got a more powerful storage system. But for us, like when we look at fiber channel versus iSCSI, we see no performance or reliability difference. If anything, there are certain things that are in iSCSI's favor at this point.
And if you really want fiber channel, Adam will talk about it later.
Adam will talk about that later. All right.
I don't really want.
Excuse me.
Yeah.
Do you support DCB? Data
DCB?
center bridging?
I'm sorry, support what?
Data center bridging.
Oh, DCB?
Yeah.
We've tested with it. We don't have it enabled for customers right now because, quite frankly, none of our customers run DCB today, and we haven't seen much benefit from it.
Okay.
So it really only helps if you've got a network that's really noisy and has a lot of packet loss, and if you have that, you probably have other problems. So yeah, we don't have that on today.
And since they're dedicated ports, you can just use pause per priority. Pause isn't necessary.
Yeah, I mean, it makes your Ethernet fabric lossless, but again, that really only helps if you have a fairly lossy Ethernet fabric, and most 10 gig fabrics that are well built don't have, much packet loss.
But now you're making the bandwidth trumps QoS argument.
But again, it's really not either. Again, unless you're oversubscribed to the point where you're dropping packets, you're not going to have that issue. I'm not going to talk too much about our UI. Very simple, very easy to use. Most people hardly ever touch it once the system's set up because our focus is really on automated management. And this is really where people get really excited about the changing in management of storage for SolidFire. All of the capabilities we talked about, everything we do is exposed through a very easy to use REST-based API that's completely comprehensive. You can literally take a SolidFire node out of a box, put it in a rack, and never log into anything at all. Just use the UI for the entire life cycle of that system. And I know you can do this because our own tools are just built on top of this API. There's nothing our tools can do magically that you can't do through this API. And all of our integrations, which are really great, are built on top of this API as well. So our VMware plugin, which is great, that you might see later. Our integration to OpenStack, which is open source. You can go actually see that in the repository today, is all based on this API, CloudStack. And so we've taken the API, we've integrated into these management stacks. So if you're using one of these platforms, if you're using OpenStack, VMware, CloudStack today, again, 98% of what you need to do is just taken care of by that platform, all the day-to-day provisioning and management activity.
Hey Dave, can we stop for a second and go back? There's a question on the internet. Do you guys have, for like VMware and such, do you guys supply your own PSP, your own multipathing
stuff?
Yeah,
we don't need it. The stuff out of the box works fine with us.
Round robin or?
Yeah, so there's, without getting into too much options, there's different options depending on the environment, and we work with all of them.
Okay,
so.
cool. Thanks.
Yep, nothing special there. We do have an optional VMware plugin that just means you don't have to go to our web interface. You can manage everything through the VMware UI. And of course, we support all the VMware primitives for block acceleration.
Cool.
So with that, I think I will hand it over to Adam to talk about some of the new stuff in Carbon. Then I'll come back and talk about the architecture.